going to be just a really quick video. I forgot that this was before we moved on to logs. And this is about exponential modeling. We could massively link this to the coronavirus again to talk about how they do all their predictions for kind of how many people they think are going to be infected and so on. So again, loads and loads of real life kind of links. Just hang on one sec, I've got a dog crying on the other side of the door. Okay, so he's happy now. Essentially, we're going to be talking about how we can use exponential functions, so functions involving e to the power of x or e to the power of kx, with maybe as complicated as something that looks like I don't know, this, to make predictions about values of y depending on values of x, and even looking at how their gradient functions behave. We now have the ability to differentiate this, so we can get this gradient function. In fact, let's do that now as a practice. What will dy by dx be for this function that I've just made up? So what happens when we differentiate a 4? That will go to 0. Then we just need to differentiate the 5e to the 7x. The 7 will come to the front and multiply by the 5, so that's going to be 35. And then we just copy this out again, 35e to the power of 7x. So I've just got one really quick example. This is the density of a pesticide in a given area of field. So P is the pesticide, and this is over time, where T is the time since the pesticide was first applied. It wants the initial density of the pesticide. So the initial density is when T is equal to 0. And when T is equal to 0, this will become e to the power of 0. E to the power of 0 is 1. So that will just be 160. The initial value in an exponential function is always this number here. If there's an extra value added on, so if it was like 160 blah 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 plus 20, the initial value would be 160 plus 20. We don't have that here, so the initial value is literally just the value that the e is being times by. That's always true. So there's my 160. It says find the density of the pesticide after 15 days. This is just a straightforward substitution. That's going to be 160 times e to the power of negative 0.006 times 15. And we can use our calculators to work this value out. We're expecting it to decrease. We know it's decreasing because this is a negative value. I'll talk more about that in a second. Let me just work out the thing whilst I've got my calculator in my hand. I'm getting a value of 146.2. So, I just mentioned that this was going to be a decreasing function. When we try and work with e as much as we can. The reason we try and work with e as much as we can is because we can differentiate it. And so knowing when we have exponential growth and decay using e is a little bit different than when we are using that b value, the base. So we will see exponential growth when k is greater than 1 this time, and we will see exponential decay when k is between, when e is greater than 0, not 1, and we'll see exponential decay when k is less than 0. So a bit different than when we had the b to the power of x. That was the exponential growth when b was bigger than 1, and exponential decay when b was between 0 and 1. a little bit different when we're working with E. So there's our 146 milligrams per metre squared. This time now it wants us to differentiate the function. So show that it can be written in the form Kp, where K is a value to be determined. So let's see how we can do that. Well, let's start by differentiating. So is it 0, 0 or 0, 0, 0? So differentiating dp by dt is going to be equal to 160, that just stays there, times by minus 0.006 e to the minus 0.006t. Now, I'm not, I am going to times those things together. 160, no I'm not. And the reason I'm not is because it wanted us to write that as something to do with P. So I want to bring P back in. So what I'm going to do is just switch these two things around and write minus 0.006 times 160 e to the minus 0.006t. And that is so that I've got my P here. P is 160 e to the minus 0.006t. So I can swap this now for P. So dp by dt equals minus 0.006p, which is what it wanted us to do. So K, in this case, is the minus 0.006. Okay, part D then says what's the significance of this value of K, or the sign of K, the fact that K is negative. Well, that just shows that there's exponential decay, because as T increases, we have less P than we had before. So this shows exponential decay, which we've kind of already said. So since K is negative, we have exponential decay. Okay, so that's just a quick example of exponential modelling. You can now work through exercise 14C, and next time we really are going to be talking about logs.